Hello everyone, today we're going to build the proportional component of our Verilog-based PID controller, the part responsible for producing the behavior that you're seeing right now. We're going to continue directly from the progress that we made in the previous two videos. If you're new to this series and you want to learn how to design a PID controller purely in Verilog, start with part 1. The link is in the video description below. Since we are only implementing the proportional component, the controller will cause the ball to oscillate back and forth instead of balancing it perfectly in the middle. This behavior is completely expected from a proportional-only controller. In the next video, we'll introduce the derivative component, which together with the proportional term will form a complete and well-behaved controller. So this here is the block diagram for the proportional controller, but before we go into it, let's do a quick recap of what we've built so far. In part 1, we designed all the circuitry responsible for taking the distance measurements and filtering out noise. The entire section for part 1 is shown right here in the green box. Here's a short clip of all the part 1 modules in action. So this is the measurement circuitry from part 1. The right 4 7-segment displays show the measured distance, and the left 4 show the desired distance. In part 2, we designed the PWM controller that drives the servo motor. That section is shown here inside of the blue box. Here's a short clip of that module in action. Now in this video, part 3, we're going to implement the remaining 3 modules needed to complete the proportional controller. These modules are the sampler, the error calculator, and the proportional response module. Once these are done, we will have a fully working proportional controller and hardware. So here's the top level module that contains everything we have built so far for part 1 and 2. In this video, we're going to complete part 3 by adding in the modules needed to implement the proportional controller. Now let's talk about the sampler module, which is the first of the 3 new modules that we need to make for the proportional controller. The sampler's main job is to take the continuous measurement stream coming in from the sensor and filtering circuitry and break it into 3 useful pieces of information, which are the new measurement, the previous measurement, and the time elapsed between 2 measurements. Those 3 values will be used by the downstream modules to compute the error and generate the proportional response. On the left, you can see the block diagram representation of the sampler, and on the right, we have the port table which lists each of the sampler's inputs and outputs. Let's walk through these signals. In is the raw 16-bit filtered distance measurement coming in from the circuitry that we built in part 1. This is the sampler's input. MP is the previous measurement. This is simply the value that came before the current sample. MN is the new measurement, the most recent value sampled from the IN input. Time is the number of clock cycles between samples, which allows us to compute the sampling interval. And lastly, done is a pulse that tells external circuits when the sampler has updated all of its outputs. This module is simple, but it provides extremely important timing and state information needed to calculate the error correctly. So this waveform shows the behavior of the sampler module. The sampler module updates its outputs once every sampling interval. Because this sampling period is fixed, the time elapsed output remains constant. The previous measurement output always reflects the value of the new measurement from the last done pulse, while the new measurement output corresponds to the input value at the current done pulse. In other words, each rising done pulse captures a new data point and shifts the old one into the previous measurement register. So now that you understand how the sampler module works, let's take a look at how the code works. So this here is the sampler module. On lines 3 to 12, we declare the module and all of its ports. Notice that on line 4, we also declare a parameter called sample cycles, which controls the sampling interval. Its default value is set to 3 million, meaning that at 100 MHz clock, the sampler will update once every 30 milliseconds. Another important detail here is that all of the output registers are initialized. In particular, time elapsed is initialized to sample cycles and every other register is initialized to 0. On lines 14 and 15, we declare two internal registers. The first is doneInt, the internal version of the done pulse, and the second is counter, which tracks how many clock cycles have elapsed since the last sample. The main logic of the sampler is in the always block starting on line 17. The if statement spanning lines 18 through 21 checks whether the counter is still less than the parameter. If it is, we simply increment the counter and force the internal done signal low. The if statement spanning lines 18 through 21 corresponds to the waiting phase of the sampler. All it does is count clock cycles until it's time to take another measurement. The else statement spanning lines 22 to 34 executes once the counter equals the parameter. At this moment, several things happen in parallel. First, the previous measurement register is assigned the value that was previously stored in new measurement. Second, the new measurement register is updated with the current input value, giving us the most recent sample. Third, the time elapsed register receives the value of the counter, which represents how many clock cycles have passed since the last sample. Fourth, the counter is reset back to 0, preparing the module for the next sampling interval. And finally, the internal doneInt register is driven high for exactly 1 clock cycle to indicate that a new sample event has occurred. Finally, on lines 36 to 38, we have a second always block that transfers the internal done pulse onto the module's done output on the falling edge of the clock. This timing shift is intentional. It ensures that the downstream circuits, which typically sample on the rising edge, receive a clean, stable done pulse, without any risk of sampling a signal that is changing on the same edge. While it's technically possible to assert and sample a done signal on the rising edge, driving it on the falling edge provides more margin and avoids potential hazards or race conditions. Now let's briefly look at the simulation of this module from the slides again, so that its behavior can be reiterated once more. So this here is the live simulation. As I go to each done pulse, you can clearly see that the new measurement is always equal to the input, which is exactly what we wanted. Additionally, the previous measurement is the shifted version of the new measurement, and the time output is always constant due to the sample rate staying the same, which was also what we wanted. So looking back at our block diagram, we've now completed the sampler module. All that remains now are the error calculator and the proportional response modules. Fortunately, since the error calculator is just a subtractor and the proportional response module is just a multiplier, we don't actually need to do anything to make these modules. We can simply instantiate the subtractor and multiplier from the fixed point section of the textbook to quickly implement these modules. Now that we have covered all three modules, let's look at the final top-level module that combines everything together. So this here is the top-level module that combines everything we've built across parts 1, 2, and now part 3. So to start, the sampler module is implemented on lines 55 to 67. We begin by declaring all of the sampler output wires on lines 55 through 58, and we instantiate the sampler itself on lines 60 to 67. The sampler takes the filtered distance measurement from part 1 and uses that as its input. You can see that connection made on line 62, where HIS filtered value is fed directly into the sampler's input value port. The parameter for the sampler is set to 3 million, written as 30 with 5 zeros appended to it, which corresponds to a 30 millisecond sampling interval at a 100 MHz clock. This determines how often a new measurement pair is generated for the proportional controller. Next, the error calculator module is implemented on lines 69 through 79. This module simply subtracts two values. First, the desired distance, which comes from 10 slide switches and is treated as an unsigned integer, and secondly, the new measurement value from the sampler, which is an unsigned 16-bit value. Since the subtractor module expects signed inputs, we need to convert these unsigned values into signed values before feeding them in. To do this, we extend each input by adding leading zeros. The switch input is 10 bits long and is padded with 7 zeros, effectively converting the switch input from an unsigned 10-bit integer into a 17-bit signed integer. The result is stored in the desired distance wire, declared at the start of the module. And the new measurement is padded with 1 zero before entering the subtractor, effectively converting it from an unsigned 16-bit integer into a 17-bit signed integer, ready to be processed by the subtractor. So in summary, both inputs must be converted into assigned format before entering the subtractor. We achieved this by padding the switch input with 7 zeros to form the desired value, and by padding the new measurement with 1 zero so that both signals match the subtractor's expected signed input format. Next, the proportional response module is implemented on lines 81 through 96. All this module does is multiply the error by the proportional gain, Kp. Since the error coming out of the error calculator is an 18-bit signed integer, the multiplier must be configured to accept inputs with 18 integer bits. We accomplish this by setting the multiplier parameters to 25, 7, and 50. These parameters configure the multiplier to use S18.7 fixed point format for both of its inputs. This means that the inputs are signed and must have 18 bits of integer and 7 bits of fraction. So to feed the error signal into the multiplier, we simply append 7 zeros to the right of the 18-bit integer. This converts the error from a signed 18-bit integer into an S18.7 fixed point number. So, to feed in the Kp constant into the multiplier, we also ensure it's in S18.7 format. We do this in its declaration at the top. The fraction parameter on line 86 specifies 7 fractional bits. We do this not because the design requires 7 fractional bits, but because the multiplier module requires a non-zero number for its parameters. We could have just as easily have chosen 5 or 10. 7 was simply a convenient choice. The output of the multiplier is the proportional response, which is a 50-bit signed fixed point value. Because the output is 50-bit wides and still uses 7 fractional bits, the resulting number is represented in S43.7 format. In other words, the output is signed and contains 43 integer bits and 7 fractional bits. So now that we've covered how all 3 modules work, the sampler, the error calculator, and the proportional response block, we can move on to the remaining support circuitry that brings the controller together. Also, as a reminder, if you need a refresher on how the multiplier or subtractor modules work, refer to the videos in the playlist discussing them in more detail. On lines 98 through 110, we have the 3-input adder. In a full PID controller, this adder would combine the proportional, integral, and derivative responses into one total output. Since we're only implementing the proportional term right now, the other 2 inputs are simply set to 0. We sign extend the proportional response so it matches the full 193-bit input of the adder, and the output of this module becomes our total response signal. The adder is configured to operate on very large S161.32 fixed point values because once we implement the derivative controller in the next video, the intermediate values can grow significantly. By making the adder extremely wide from the beginning, we guarantee that no matter how large the intermediate P, I, or D terms become, we will never lose precision or run into overflow issues. And finally, before sending the value into the PWM module, we need to resize the output. The PWM controller only accepts a 42-bit signed input, but total response is a much larger S161.32 value. Lines 114 through 124 handle this by first extracting the upper 161 bits into PID int, clamping that range between a maximum and minimum value, and then taking the lower 42 bits of the clamped results. This produces response clamped, a properly sized and safe value for the PWM module. And lastly, on line 130, we have the display module, which shows both the measured value and the desired value on the 7 segments. Since this isn't part of the core PID logic, we won't be discussing it here. So there you have it, we've now fully designed the proportional component of our Verilog-based PID controller. In the next video, we'll complete the controller by adding in the derivative component, which will make the system fully functional and stable. If you found this video helpful, be sure to like, comment, and subscribe. And if you want the project files, they're included with the textbook linked below. Thanks for watching, and I'll see you in the next one.